There is a kind of water sitting quietly in oceans, rivers, and the vapor in your own breath, and a small fraction of it is older than every star you have ever looked at. It formed within the first few minutes of the universe, long before the first galaxy ever switched on. That water carries a heavier version of hydrogen called deuterium, one extra neutron tucked into its nucleus, and almost none of it was made afterward. Stars are surprisingly good at destroying deuterium, not making it, so nearly every atom of it in the universe today is a leftover from a single, incredibly brief window right after the Big Bang. So here is a question worth sitting with for a second. If nothing since has topped up the supply, then the amount of deuterium floating around the cosmos today is basically a fossil record, a direct fingerprint of conditions in the first few minutes of time. And fossils, read carefully, can tell you whether the story you have been telling about the past is actually right. Physicists trust the Big Bang model for three separate reasons. Not one. Distant galaxies are all rushing away from us, exactly as an expanding universe would look. There is a faint afterglow of heat filling the entire sky, the leftover light from the moment the universe first turned transparent. And the third pillar is the quietest one, the exact recipe of light elements: hydrogen, helium, deuterium, and a trace of lithium. That Sutria is correct. That third pillar has a surprisingly old paper trail. In the late 1940s, physicists worked out on paper how hot, dense matter in the earliest universe would have fused into the first atomic nuclei before a single star had switched on. It reads almost like a recipe. Start with free protons and neutrons, let the universe expand and cool for a few minutes, and see what nuclei survive. So what actually happens inside that recipe? For the first fraction of a second, the universe was too hot and chaotic for any nucleus to survive. Protons and neutrons collided and split apart almost as fast as they could stick together. Physicists call this the deuterium bottleneck, and only once the universe cooled below a certain temperature could deuterium nuclei finally survive long enough to become a stepping stone toward helium nuclei, Almost all of the deuterium made in that narrow window still gets partially destroyed before the process finishes, burned into helium and other light nuclei. What survives is a tiny, precisely calculable leftover, and that leftover the fossil scientists can still measure today, in gas clouds so ancient and so untouched by starlight that they still carry almost pure Big Bang chemistry. To read that fossil, astronomers point telescopes at the light of extremely distant quasars and look for the faint shadow that primordial gas clouds cast on that light as it passes through them on its way to Earth. Buried in that shadow is the deuterium fingerprint of the early universe, measured with a precision that would be almost absurd for anything closer to home. For decades, that fingerprint matched the recipe astonishingly well. It became one of the strongest confirmations science has ever had, a case of a 70-year-old prediction lining up with reality down to fine detail. But recently, that agreement has started to wobble. Just slightly, in a way that some cosmologists cannot quite ignore. Here is where a second, completely unrelated puzzle enters the story. For years, cosmologists have been arguing about a totally different number, exactly how fast the universe is expanding right now, today. Measure it one way, using nearby stars and galaxies, and you get one answer. Measure it another way, using the faint afterglow light from the early universe, and you get a slightly different answer. Neither measurement seems to be wrong, and nobody has found the mistake, so the disagreement is own nickname among physicists. Some researchers have proposed a fix. What if, for a brief moment, deep in the universe's infancy, some extra source of energy gave space an added push, speeding up the expansion just enough to explain the mismatch? It is a strange idea, but it is testable, because that same brief push would leave fingerprints on other things too, including the exact recipe for deuterium. And that is where the two mysteries collide. If you tune the early universe to fix the expansion puzzle, the amount of deuterium the recipe predicts quietly shifts along with it, and it starts drifting away from what telescopes actually see in those ancient gas clouds. Have you ever wondered why some of the water sitting on Earth right now is technically older than the Sun? It sounds like a trick question, but it is not. The Sun and the planets formed together out of a swirling cloud of gas and dust roughly 9 billion years after the Big Bang. But the deuterium inside that cloud, the heavy hydrogen that ended up locked into water molecules on this planet, was already ancient by then. It had been drifting through space since the universe was only minutes old. So the next glass of water you drink almost certainly contains a few molecules that are, quite literally, fossils from the birth of the universe, untouched and unchanged for over 13 billion years. Which brings the story back to the puzzle at hand. If that fossil is this reliable, this old, and is precisely measurable, then a mismatch between what it says and what the standard recipe predicts is not something scientists can just shrug off. Think about it like baking a cake from a recipe that has been trusted for generations. Every time you follow it, the result comes out right, until one day, using a slightly different oven temperature that other evidence says should be correct, the cake comes out a little underdone. Do you assume your thermometer is broken? Or do you start wondering if the recipe itself needs an extra ingredient nobody wrote down? That is roughly the position cosmologists found themselves in. Using the oven temperature suggested by the leftover heat of the Big Bang, the standard recipe undercooks deuterium, not by a lot, but by enough, and consistently enough, that pure chance becomes a less and less comfortable explanation. The mismatch is small when you use the most conservative numbers, but it grows sharply worse in exactly the models that try to fix that other puzzle, the expansion speed disagreement, by speeding up the early universe. In those models, the deuterium gap stops looking like noise and starts looking like a real signal. If you have been enjoying this kind of story, real science quietly chasing down a mismatch that most people will never hear about, hit subscribe because we dig into a new one. Like it every week. Now, back to the part nobody had actually tested yet. So a team of researchers set out to test a very specific idea. What if the fossil record is not lying, and the standard recipe really is missing something? Their hypothesis was surprisingly specific. Not a permanent change to the laws of physics, but a brief, temporary one. Imagine some unknown field of energy that briefly switched on, gave the expanding universe a short extra push lasting only a few minutes, right in the exact window when deuterium was being forged and partly destroyed, and then switched back off and faded away, leaving no other trace. So what happens if you actually build that idea into a model of the early universe and run the numbers? Using an updated computer model of the universe's first minutes, the researchers simulated exactly that kind of temporary push and compared it against the standard unmodified recipe and against a simpler idea some other physicists had floated before. A constant, ongoing boost of extra radiation throughout the whole process rather than a brief, timed one. The constant boost failed almost immediately. It did nudge the deuterium numbers in the right direction. But it also sped up an earlier stage of the process too aggressively, overproducing helium in a way that broke a completely different, very well-measured number. Fixing one fossil by breaking another is not a fix at all. The brief, perfectly timed push told a different story, because it only switched on for a few minutes, right around the moment deuterium was being finished off. It left the helium numbers almost completely untouched, while still nudging deuterium back toward what telescopes actually observe. And the size of that timed push was not small. To make the numbers line up, the researchers found the early universe needed to expand roughly 9% faster than the standard picture assumes for just a few critical minutes. With that adjustment in place, the mismatch that had been growing between the deuterium fossil and the early universe's expansion speed nearly vanished. What had looked like a real, hard-to-ignore disagreement shrank down to something so small it falls comfortably within ordinary scientific noise. The researchers behind this are careful not to oversell it. Their own conclusion is that this is a hint, not proof. The deuterium measurement itself still carries some disagreement among the astronomers who study it, and a slightly different, more recent reading of that fossil softens the mismatch, even without any new physics at all. Extraordinary claims still need much stronger evidence before anyone calls this settled. But if a hidden temporary field really did switch on for a few minutes in the universe's infancy, it would not be the first time cosmologists have needed one. A similar kind of field is already thought to have driven the universe's explosive first fraction of a second, and another is thought to be quietly stretching space apart right now, today, as you watch this. Which raises a genuinely strange possibility. What if these are not three separate, unrelated coincidences, but three glimpses of the same kind of hidden physics, switching on and off at different chapters of the universe's history, each one leaving its own fossil behind for us to eventually find? You can find the full analysis, including every number and every model tested, linked in the description below. So the next time someone tells you the Big Bang is settled science with nothing left to check, remember the water in your glass. Some of it has been keeping a secret for 13 billion years, and we may have only just started learning how to read it.